Okay, so I will be with you in the solar thermal energy system. Today, inshallah, I will talk about the course in general. So it will be introduction to solar thermal energy system, about the technology, the difference of this technology from the others. It will be general talking about the course itself, the contents of the course, the classification of the course, the objective of our course, the grading of the course, how it will be. So it will be general about the syllabus and introduction to the course. I will be grateful if you have any questions, you raise your hand and ask. If you have any suggestion, then you can suggest it, then to make the things going easily, inshallah, through the semester. So today it's more than I will want to listen from you if you have anything after we finish the introduction of the course. Okay. From next lecture, inshallah, we will start chapter 1, but today is almost introductions and to know what is the solar thermal energy system. Anyone has an idea about the solar thermal energy system? Anyone has an idea about this course? Yes, Sultan.
Yes, Doctor.
So anyone can express, or do you have an idea about the course? What do you expect to have in the course? What does this course mean?
We make use of the heat that comes from the sunlight to generate electricity.
So we're going to use the heat coming from the sunlight to generate electricity. So we said that the main purpose is to generate electricity. So this is one of the purpose, or one of the things that we're going to use it within the solar thermal. However, the difference between the solar thermal energy system and the other systems, such as renewable wind system or PV voltaic system, is that the PV, we directly convert the solar radiations to electricity. But here, for the solar thermal, we convert the solar energy to thermal, which means that I'm going to have thermal energy, then I can direct the use of this energy to whatever I want. I can use it for generating electricity. I can use it for industrial heating. So this is the main difference. Here I don't use just the solar thermal for generating electricity, but now I'm going to have the thermal energy, then I use it as I want. Okay. So here, thank you, Muaz. I will start talking about the solar thermal energy system in general, also introduction here. 1 minute. So here we have solar radiations. As I said, we're going to convert it to energy or thermal energy. So to convert it to thermal energy, we want something in between, which is the working fluid. So the main part here, we need for solar thermal energy, the solar collectors and the working fluid. And this is the difference from the other concepts, such as the PV. So for PV or solar energy conversion, we know that we have two methods. I'm going to convert the solar energy to thermal energy or electricity generation. This one is direct. We're going directly to use photovoltaic and it converts the solar energy or solar light to energy. But here I'm using the heat from the output from the solar thermal or solar energy conversion due to thermal energy. It will be classified according to the temperature. So sometimes I can collect low temperatures or low thermal energy. When we said low, that mean will be less than 100 degrees centigrade. Otherwise, sometimes we can collect very high temperatures depending on the type of the collector that I use. And in this case, we can say it will be more than 400 degrees centigrade. So the thermal energy, the collected heat, classified to many things. One of them according to the temperature, as low temperature when the temperature less than 100 degrees, high temperatures when the temperature is more than 400 degrees, or in between or medium temperature when the temperature between 100 and 400 degrees. According to the collected heat, we're going to make the application, or we're going to use it. So it will be applied according to the collected heat. If I have heats or temperatures less than 100 degrees, so in this case, I'm not going to generate electricity. So I'm going to use it for heating, such as domestic heating, domestic water heating, solar pool, or space heating. So it's only for heating purpose, which need less than 100 degrees, 65, 45, depend on the thing. Okay. And as I said, the low temperatures or high temperature depending on the type of the collector. When we here, I said I have the working fluid and I have the solar collector. So this solar collector, depending on this solar collector, we will have the temperatures range. If I have using flat plate collector or solar bond, in this case, the collected heat will be less than 100 degrees centigrade. If I using flat plate collectors or solar bond. The flat plate collectors, the average of the temperatures up to 40, 60, up to 90 sometimes, depending on the material of the absorber in many other parameters. Okay, so but maximum up to 100 if it's reached. So this one when we use the flat plate collector. Later, we're going to talk about the flat plate collector in details, how it consists, this one, of the, this type of the low temperature. The other one, solar bond. Before that, I will say, okay, this is the application of the flat plate collector, which most of you already know about it, maybe from the introduction of engineering course. Domestic water heating, swimming pool, space heating, drying agricultural products, many applications which need this low temperature. Also, from the low temperature, we can use solar bond, and solar bond usually used for heat storage. Any one of you knows what the meaning of the solar bond? Maybe a flat plate collector, I think most of you know about it. But solar bond, have you heard about solar bond?
We use water, and I think we put salt or any other material that stores the heat, something like that.
Okay, so the solar bond actually, something like that, as you said, it is actually a pool of salt water. So we have a containers, something like that. Okay, this one is same like a pool. 1 minute, please. It's not something happening here. Okay. Okay. Something like that here. I have a pool. This pool have a salt water with different concentration. So usually it's divided into 3 main zones. This is the first zone, the second zone here, and here I have the third zone. And in each zone, I will have water. All of these one have a water, but the difference is this salt water has different concentration. So in here, in the last one, which we call it the storage zone, we have high salinity water. So we have here a water with concentration in salt or saturated water. So here we have high or water with high concentration of salt. In the other zone, which will be bigger than, or the biggest zone here, which we call it non-convective zone. So in this zone, we divided the waters to say 3 or 4 layers, and each layer have its own concentration. So what I have, once I have different concentration, that means will have different density. Since we have different density, so the salt water forms a vertical salinity or natural, because they have different salinity. So different salinity or different density. So I have vertical difference here, salinity difference. So in this layer, which is non-convective zone, I have also water with different concentration of salt, and the last one here, which we call it just only, it will have fresh water. So what will happen? The sun or the radiation will start to penetrate from the first zone up to the last one. Is solar radiation. It's just only penetration of the solar radiation. When it reaches this zone, it will absorb the heat from the radiations or from the solar radiation. And this here, the temperature will have highest temperature. Say it's reached sometimes 60 degree or 70, depending on the size and many parameters here. So here I have 60 degree of water, and this one will be stored because this one non-convective zone, so I'm not going to lose the heat from this layer, and it will be work as storage. When we need high temperature, just we're going to take this water, we're going to use with the heat exchanger or organic Rankine cycle. We use whatever we want, then we return it here and it will be collected again. So the solar bond mainly used as heat storage. This is for the low temperature solar energy. The second one, which is medium temperature, the temperature is between 100 up to 400. And here we're using this type of the collector, evacuated tube collector, compound parabolic collector, direct absorber solar collector. So the difference, maybe evacuated, you know it, which is normal, same like flat plate collector or tube absorber, but the difference between the evacuated and the flat plate collector here, we evacuate the area between the absorber and the glass. When you evacuate the area between the absorber and the glass, when we said evacuate, that means we are going to remove the air. Since I removed the air, that means I will minimize the heat loss by convection. So here, since we reduce the losses, that means we're going to increase the temperature. Okay, so because of that, in this time, we'll have temperature more than 100 degree. Also, the compound parabolic collectors, this is also another design, and it will give us a high temperature. The direct absorber solar collector here will have, from the word direct absorber solar collectors, means that instead of using absorber, I'm going to use the working fluid itself as an absorber. What does it mean? If you go, if I show you the first slide here, I said here I have glass. Then we have in that thing, we have glass. Then we have absorber. This is the cover, which is the glass. Here is the absorber, which is the black panel to absorb the heat. Then this black panel is attached to, say, tubes, and the heat absorbed because of the conduction or attachment between this one, which is the tubes, and the plate. The heat will be conducted from the plate to the tube, and the fluid will be inside here. So I'm heating the fluid indirectly. But for the direct absorber solar collector here, what will happen here? I will have fluid here. So this fluid with a certain properties, and the sun radiation will penetrate from the glass directly. It will face this fluid. So what will happen? It will directly heat the fluid. Because of that, we said direct absorber, which means that the fluid itself will work as an absorber. So to make this one become good or to work efficiently, normally we're using this fluid, we add to it some particles, nanoparticles, to increase the properties here, which means that the thermal conductivity, the many things here which will increase the storage or the absorption of the fluid. We increase most probably the absorptivity. So we sometimes we add carbon nanoparticles, so it will make it absorb more heat. It will increase the absorptivity. We increase the thermal conductivity, many properties. So here in this type, the fluid itself will work as the working fluid. It have advantage and disadvantage, but one of the advantage of it, it's well, if you see before I said that I have the absorber attached to the tubes. So what's happened when the heat is transferred from the absorber to the fluid inside the pipe, I will have some heat losses, because you know that we have something same, I have a medium between them. But here it's directly, so I'm reducing also the losses. Because of that, we have sometimes temperatures more than 100. So depending on the design of the solar collector, we find the temperature, or on the type of the solar collector, we can obtain higher temperatures. And according to the temperature that we obtain, we're going to use it. So here, if I have low temperature, directly I'm going to use it domestic. I cannot take a bath with 100 degree water, but we can take it with 45, 35, depending. We can wash with these temperatures, clothes with this thing using for laundry, whatever. But for the medium here, temperature up to 200, something like that, we can use it for some technologies such as absorption cooling, because it's need temperature up to 200, used for absorptions, for adsorption cooling, for evaporative cooling, those needs temperature more than 100. Also for some industrial process, sterilization, this one needs temperature up to 200, 300, depending on the last one, which is high temperature. And since I obtained very high temperatures, directly we're going to use it for electrical generation. And this high temperature obtained by using the CSP, which is concentrating solar power. Why you obtain this high temperature? Because we're going, the same thing here, we're going to use absorber or receiver, we're going to use sometimes cover, but the thing here, the additional things here is we're going to use concentrations, or we are going to concentrate the solar radiations and direct it to the receiver. So here I will concentrate more solar radiations instead of using the, we have beam radiations and diffuse, whatever. So I'm going to use more of the beam and direct it to our receiver. In this case, we'll have high temperature from 400 up to 1000, sometimes on 500 or 1500. So when I have high temperatures, I will just going to connect it to the turbine, steam turbine. I'm going to use it to generate electricity. The main difference between, or the main features of the solar thermal, and that it's make it more applicable for mass utility or mass productions. When I said mass production, that's mean I'm going to be used for 1 month and say numbers of the houses or numbers of or a village, something like that. It can be integrated to the thermal energy storage. What does mean that it's integrated to thermal energy storage? Since it will be integrated to thermal energy storage, that's mean if I don't have sun, or I don't have solar radiation during the night or at early morning, still we can use the renewable energy. Why? Because I will have excess. Sometimes at the noon we have high solar radiation. So this excess of solar radiation can be stored, used thermal storage system, then will be used when I don't have sun radiation. So because of that, the CSB or the thermal energy storage has a good feature that it can be integrated to thermal energy storage and make it can be continuous use of it, continuous for a user, and make it has high dispatchability. Okay. In the other things, say for PV and wind, they are cheap to some extent. But at the same time, if I don't have radiation, so what will happen? We're going to have problem for the user, or we cannot provide the user with the required load he needed. So we have to go to other things. So we have at the grid problem, that means we don't have stability for the grid. Because of that, they said sometimes the thermal energy, but it's not thermal energy. Thermal energy for CSB mainly with the storage system, it's better than using the B. If I'm using the PV, the solar CSB, without storage system, in this case, I should go to PV. However, if I'm going to include the thermal energy storage, so in this case, we have to go to CSB because it will give us double the power that we can find it from the PV. Normally, we said if I want electricity, I will go to for PV. It's easy installed. It's have no moving parts. Many things within the PV, it's have a features. But actually, when we come to the storage system, we go to the CSB. But with the storage system, and it can provide double the amount that can be provided by the PV. So here I'm talking about I just introduced the type of solar collectors in terms of output, temperature output, as well as some of the applications of the solar collectors and the main difference between the thermal energy and other renewable energy, such as wind and PV. Okay, that's mean because the thermal energy can be stored for more than one things, while the wind and PV only for electrical generations. The other part which is important for the thermal energy is, as I said here, we have collector. You see this figure, we have collectors and we have working fluid. So now if we go to talk about the working fluid, so working fluid also is a main part in the solar thermal. Why? Because this is the part which will absorb the heat, and this is which is the working fluid, which will transfer the heat from part to part or from an item to item. So normally for the heat transfer fluid, we're using, which we call it the working fluid here, we call it HTF, means that heat transfer fluid. We need this heat transfer fluid or the working fluid with a certain properties. So we have different type of the heat transfer fluid. Some of them, they are used for low and medium temperatures, and some of them they can be used for high temperatures, depending on their stability. If you see here, for example, sure, the water can be used for anything. It's easy to be stable. It's no problem with it. But sometimes we increase the property. For example, here, I have here water. The water is very ideal. It has very high specific heat. You see here, 4.2. It is non-toxic, so it is very environment use, so I don't have any problem with it. Okay. However, and this is the properties of the water. However, sometimes we're going to make a mixture between the water and the ethylene glycol. Why? Because we want to improve some of the properties. What type of properties that I needed for the heat transfer fluid? One of them is the operating temperatures, operating range temperature. What does this mean? The operating range that's from the freezing to boiling. So the water normally freezes at what temperature? At 0. But if I make a mixture between the water and EG, it will freeze at which temperature? At minus 36, which means that I have increased the range or the operating temperature. Instead of working from 0, say, to 100, I can work from minus 36 to, say, 100, which means that I'm increasing the operating range of temperature. This is one of the properties we care about, which is the freezing temperature. Also, we care about the stability. For here, for isoglykol, what happened? It is stable up to 120 type. If I have temperatures more than 120, what will happen? It will start to have some instability or chemical interaction, whatever. So it can start to degrade. And these degradations will cause some correction issues. So in this case, I am limiting to use this working fluid to what? To the low temperature solar collector. So this is which connecting the output to the working fluid. Depending on the working fluid, its stability, I cannot use the isoglykol to the, say, CSP. Why? Because CSP will heat the working fluid up to, say, 300. So 400, when the fluid reach 120, it will start to be unstable, and this will cause problem. Okay, so this is some of the common properties. This example is just only for heat transfer fluid. Here for propylene glycol, it can be stable at 150, which means more than this, but it still have some remark. Sometimes it's toxic, okay, and it have, but once it's toxic actually, but it's less toxic than the EG water. We have another one here, the mineral oil. Here it can be stable up to 220. At the same time, its freezing temperature up to minus 20, but actually it's toxic. So when we use it, we have to take care about the environment minutes we have it, okay? And it have, if you see here, it have high viscosity, okay? So high viscosity, which means that it will need more pumping power, okay? And it's here have, say, specific heat, maybe it's low specific heat. So depending on the applications, I'm going to choose the heat transfer fluid. If I go for the high temperature collectors, that means I should use heat transfer fluid that can be stable up to 600, 400, these temperatures. So because of that, if you see here, the synthetic oil, it can be stable up to 350. So it can be used in the linear Frenzel. It can be used in the parabolic draft, because these sometimes they heat up to 350, up to 400, but it depends on the thing. But maximum sometime up to 350. So here molten salt give us very wide range of operation. It's reached up to 600 stability. But you see here, what is the freezing point for it? It will start to freeze at 120 temperature, which means that we have to take care of this one. So it has a certain operating temperature. This is another type. We have liquid metals. They can be stable up to 890, and they start to freeze at 89. So this is common properties or general talking about the heat transfer fluid. The two important things for the solar thermal, your collector, depending on the design of the collector or on the type of the collector, you will have, or your gain, your output temperatures, and the output temperatures will define which application you're going to use it. So you can start from the bottom. That means I want to start from the application. I want to use solar thermal at heating purpose. That means I will go for low temperature solar collector. That means I will go for this type of the heat transfer fluid. Okay, so according this all connecting together. The applications, the type of the solar collector, the heat transfer fluid. So this was general talking about the solar thermal, or introduction about the solar thermal. We can go also or talk about the importance. What is the importance of this course? Okay, as we see here, we're going to harvest the solar energy, convert it into heat. This is very important when you said convert it into heat. Why it is important convert it to heat? Because it will give me integration. That means I can use it. I have heat. Then, depending on your application, I want it for electricity generation, you can use it. I want it for heating, I can use it. I have excess of heat, so it's not going to be thrown out. No, it will be used for this and this at the same time, for generating electricity, and the other can be used for heating application or industrial heating. So this one, the important is convert the solar energy into heat, but at the same time, it needs to be improved. So we have challenge for this technology, such as we need to increase the efficiency. How we can increase the efficiency? We starting by the flat plate collector. Okay, and we start to the output from the flat plate collector, say 70 degree or 60, say. So I want to increase the output. How can I increase it and the efficiency? Increasing the output and the efficiency means reducing the losses. How can I reduce the losses? I will go from the flat plate collector for evacuated collector. So when I said evacuated collector, I will evacuate this area between the absorber and the cover. What will happen here? I have already that means I will reduce the heat loss by convection. So instead of getting output 70%, I can 70 degree, I can find say 120. So here I have increased the output as well as increasing the efficiency. Why? Because the efficiency, as you know, it is the output over the input. The input is constant, which is coming from the sun. The output here, I have already increased it. That means will increase my efficiency. So this one, the first one is increasing the efficiency, and depending, this means that we can change the design, we can change many things. It's open area for research. Whatever you change, whatever parameter you can change, we can even changing the heat transfer properties. This also can increase the efficiency because I may have some heat transfer that have high absorptivity. If I'm working with the direct absorber, so collector, I have heat transfer fluid with high thermal conductivity. So this means that I'm going to increase the output temperature. So this is an open area. To increasing the efficiency, that means the input and output, or output and input. That means I'm going to increase, I'm going to work in many parameters. The input and the output, as I said here, temperature, useful energy, input, same here. We can increase it or enhance it by using concentrating. This is will increase the input also. The other here, the energy storage. Energy storage, as we said, we're going to integrate, or we can already integrate the thermal or the CSP technology to storage system. Okay, and here I can use storage system depending on the time. I can use storage system, store energy for 5 hours, or for 7 hours, for 12 hours. Whenever I have increasing the hour of storage, that means I'm going to depend more on the renewable energy. How it comes? If I have the sun, say it's this, from sunrise, sun to sunset, say it's 12 hours, for example. So I have the day is 24 hours. 12 hours I have already, the sun is available, so I'm going to use direct from the sun. The other 12 hours I don't have sun, which means that I have to go to the fossil fuel. But if I have a storage system safe with 6 hours, that's mean I will start to work with my storage system, which already stored the energy from the sun, which means that I'm already depend on the sun for 18 hours. 12 from the sun, 6 from the storage system, which already took its energy from the sun. So here I'm increasing dependency on the solar energy or renewable energy. So this one also has main challenges. We can improve the storage system by many things. We can use the capacity, and this one we'll talk about it inshallah at the chapter of the storage system for CSP. We find how we can improve the storage system. Instead of using 2 tanks, we can use 1 tank. Instead, we can change the heat transfer fluid. We can change the storage media, many things. We can talk about it later, inshallah, in this part. Okay. Also, the economy in conversion and storage, how we can, instead of using 2 tanks, we can use 1 tank. So what will happen here? I will reduce the cost of the storage. At the same time, I will still have high conversion from the sun to thermal, or more dependence on the solar. So this is also another part we're going to talk about it when we talk about the storage system. Okay, so all these part we'll talk about it later, inshallah. Here also we have area of potential. Some of them the absorber material. So instead of using normal absorber, just black paint or plate that is already painted with the black color to absorb solar radiation, we can enhance this black paint to make the absorber absorb high absorptivity, or has high absorptivity as well as low emissivity. So if it's have low emissivity, it will contain, or it will keep the absorptivity. So in this one and this type we call it selective materials or selective absorber. We will talk about it later. The glazing also, we try to use some glazing that have low emissivity, at the same time high transmittivity. So I want more radiation to be transmitted through the glass, but less to be emissivity or emitted out. So I want to keep the transmitted radiation. So this is also another thing, we can talk about it later. Insulation and space between absorber and glazing. So sometimes if you increase the space between, here this one, this is the cover, and here plate. If I increase the space between the cover and the cover and the absorber, so what will happen here? It should be, sometimes I have high space, that means sometimes I have more losses. If I have very low space, also it have another advantage or disadvantage. So what is the optimum space between the cover and the plate? This is one of the things that can be taken into consideration when we talk about the potential of improvement or many. So this is all in general areas. When I'm talking about different areas for research or for improving the properties here. 1 minute. Another part here, PV integration with solar thermal application. Have you heard about the integration of solar or PV and solar thermal? I will ask you in another way. PV and solar, both of them working in sun depending on the sun. Right. Why we integrate the PV with the solar thermal? What is the feature we're going to get it?
While using PV, we can generate electricity directly, And for the solar thermal, we can use it for heating purposes, or if it was extra, we can store it and use it later at night or any other time.
So actually, what is the main purpose? So that's mean from the integration. You already said it, but I just want one word. What is the to cool the PV? No, Sultan. What is the main? I have now talking about the PV and solar. I said there is one feature. Yes, Fandi. It's the feature of a storage system. Okay, because as I said, both of them, they are working on sun. So if I don't have sun, both of them are going to stop. But if I make an integration between the solar PV and the thermal, I cannot make integration in terms of process. Why? Because PV already going to use the light and convert it, as you know, as electrical, whatever, and going to connect it directly to the grid. But the solar thermal, it will convert the energy to heat. Okay, so if I have excess heat, or when I'm going to use the solar thermal to convert the heat, and I'm going to store this heat. So the integration of PV and solar thermal, it's not going to be in the process. No, it will be in the term of the grid, because when the PV not working, the solar thermal, or mainly the storage system that already used by solar CSB, it will start to work. So the integration between the PV and solar thermal, it will be in terms of grid. Also, we can integrate the wind and CSB in terms of grid, but we can integrate solar thermal and say biomass or solar thermal and fossil fuel in terms of process, how it's come. I will just explain it. Just let me clear these things. Okay, it will be more clear now. Here, for the CSB, okay, what we do actually, we're going to heat the fluid, whatever, everything is happened. Then we're going to take this one and going to Rankine cycle, turbine, whatever happened here. Type. For the biomass, what we have, also we're going to heat the biomass, whatever, and we take the heat and we're going to connect it where? To the turbine. So we have something common between the solar thermal and other thermal process to generate electricity, such as biomass, fossil fuel, coal. All these, they're going to use, sure, condenser. They are going to use turbine. This is two, or mainly going to be used in both of them. So we can integrate them in terms of the components. So this can lead to reductions of the main cost for the CSP. This is just in general talking about the integration. So we can integrate CSP actually to PV, to fossil fuel, to biomass, to wind, using the features of the integration of the storage system. But actually, when we integrate it to fossil fuel, we're not going to use the feature of the CSP, because actually fossil fuel is available. So you need the storage system. Here, if we use this integration, we're going to use it to reduce the CO2 emission, to reduce the fossil fuel consumption. So it will be mainly for environmental aspect. Okay, so this is one of the features of the CSB, the integrations, which is very interesting part, by the way. I don't know, we don't have it here in the course, but in general, it's very interesting to read about the integration between different renewable energy. Then you can see that what is already missed here can be completed here. So they're making a very good integrations between the different renewable energy. Another here, just this, the following slide, I will show you some of the, I just bring them from the internet, some of the solar thermal power stations already operational. If you see here, 1 minute, I will increase this one. Okay, so if you see here, in many different countries, such as here, and this at least 50 megawatt capacity. So you find here in Noor CSP power plant, it is in Morocco, and it has almost 510 megawatt. I want you to see what is the type of the technology used. Just concentrate in this one. So you find here parabolic trough. Here you find solar tower, parabolic trough, parabolic trough, parabolic trough. They're different. All these technologies depend. If you see the other slide, I will show you. So the most two commercial CSP is parabolic trough and solar tower. Why? Because up to now, these two technologies prove that they are so successful in integrated with the storage system. The solar dish, it can provide us with a very, very high temperature. It has high efficiency, but unfortunately, up to now, it cannot be integrated to the storage system. So this, which make it lacking the others. Linear differential also, it's not that much integrated with the storage system, but some of them they work. But here, parabolic trough and solar tower already they working within the system. Just see this one. If you see for the Noor, the country Morocco, and here is the type of the control, the technology. If you go to the notice and reference, you find here, okay, they have 3 phases, no problem. So what you see here, 160 megawatt with 3 hours heat storage. So here they included the storage. In the other one, they have 200 megawatt phase 2 with 7 hours heat storage. So can you imagine 7 hours, which means that if it's working directly from the sun, say for 12 hours, and it will work directly from the storage for 7 hours, that means how many hours will be from renewable energy? It's almost 19 hours. Only 5 hours can be worked from the fossil fuel. Okay, so this is very good options to reduce the emission, to work with it. So you go through this, you will find many of the examples. I already bring them here. You can find this in different countries. Okay, this is also operational solar thermal in India and Spain, different countries here. Okay, it's still here. We find, and this is the load of them, 175. This is the I bring just up to 50. We have more and we have less. Up to here and here in Saudi Arabia. In Saudi Arabia, you see this one. Also, if you see the technologies, all power, parabolic trough, solar tower, parabolic trough. But if you see this one, if you see with me, Saudi Arabia, okay, 50. If you see this word, ISCC, you know this meaning? I for integrated, S for solar, C for combined, and the other C for combined cycle. Okay, so here this is integrate. They making integrations between the solar and the combined cycle. If you remember the combined cycle, for those who took already the design, it is the one that is working with the gas, natural gas. So here they make an integration between fossil fuel or the natural gas and the solar. So the main operation or the main purpose will be to reduce the consumption of the fossil fuel or the natural gas, to reduce the emission. So this is one of the types. So because of that, we see solar thermal can integrate with other power plant, especially the thermal power plant. And it's here, it's already operated, by the way. It's commercial operation started in 2018 with 50 megawatt solar. So that's mean we have still, it's already there. There is many of the cycles or many of the power plant already depend on the solar, okay? And still we have here, this is under constructions. One of them here is Mohammed bin Rashid Al Maktoum in Dubai. So here it will be expected to be this year, inshallah. And this one also, if you see this one, it has 600 megawatt output, the technology power parabolic trough, and 100 solar towers. So they are using two technologies, solar tower and parabolic with, if you see this word, and you see it, 15 hours heat storage, which means that almost maybe 100% it will be from the solar energy, since they are using the heat storage. And this is another type. Okay, so those were just examples of some solar thermal stations already in operation and the other on constructions. Now, if I go here, this is the main topic which we're going to cover within this course. We're going to cover introduction to solar radiation. This will be in chapter 1, okay, which will take maybe 1 week. Part of this chapter already you have taken in the BV. For those who does not take the BV, don't worry, I will go in details also for this one. Okay. The second chapter will be heat transfer concept and properties of material for solar application. This chapter mainly will be divided to, you can say that, to two parts. First part will talk about the heat transfer concept, and I will concentrate, or we will concentrate on the radiation mainly. Okay, and in the radiation we're going to concentrate in the spectrum. Why my radiation? Because we need to know the properties of the material, such as transmittivity, absorptivity, and reflectivity. But here we're going to talk about the properties for spectral, which means that related to a certain wavelength. Okay. Also, the other part will be how to calculate the solar radiation. It's actually equations, and we're just going to apply them. It's not that much difficult. Maybe you will see that equation and you start to be to affirm it, but don't worry. When you start to apply it, it will be, you find that it's just equation, you're going to apply it. So it's not that much habit, inshallah. The third chapter will be introduction to domestic solar thermal applications. So we'll talk about thermal applications, or the thermal, same like here, I'm talking about the type of the solar collectors, the application of the solar collectors. It's almost same like this lecture or this introduction, but in more details. Okay. The fourth chapter will be solar flat plate collector. So we start to go in details to solar flat plate collectors. How is the heat is transferred within this flat plate collector? How we can find the efficiency and the useful energy from the flat plate collector. Okay, this is our target, to find or to evaluate efficiency and the output or useful energy. After that, chapter 5 will be the solar thermal and storage system for low temperature, and this will be connected to the flat plate collector. As we said, low temperature is less than 100. So what is the storage? Okay, so it will be connected chapter 4 to 5. So here up to 5, 4 and 5, we're talking about the low temperature and the storage system. Chapter 6, we talk about we maybe use programming here. So we'll talk about the simulation, the modeling, and hopefully we use TRANSIS, which is transient system simulations. Then the last chapters, or the other chapters, the last chapter 6, 7, and 8, 7, 8, and 9, those will be concentrated on the high temperature solar collectors. So we're going to talk about the different 4 technologies, the difference between these 4 technologies, and the storage system for this technology. Okay, so this is the topics that we will cover, inshallah, within the semester. Most probably by the chapter 4 here, it will be normally our midterm will be up to chapter 4. But now, depending on the situation, but this is the normal things. So we're going to start, hopefully we continue we finish up to chapter 4 by the week 9 or 8, okay, where the midterm, which should be done within these things, within these weeks, okay. The other will be for the final, or will be after the midterm. This is the course objective, and you will see, inshallah, later. So we have, our objective is to, did we choose a date for the midterm? I don't do it now because I'm not sure. So just let us to confirm what will happen. It will be face-to-face, or it will be online. So maybe next week, inshallah, just let us organize with the department. So inshallah, okay. So the course objective, this is the objective of the course. As you will see, it's almost I cover it. We're going to talk about the solar radiation and the performance of solar collector. As we say, that will be in chapter 4 and 5, talking about the high temperature solar radiations, which will be within the last chapter, and ability to determine the economic factor and perform economic analysis for solar energy system. This is the objective of the course. Already I talk about it in general. And here is the textbook. I use it. This one, most of the slide is from this book. Okay, it's Caligaro for series at 2013. Okay, so this is the textbook, and most of the things I'm using this book and this book, actually, these two. Most of the slides from here, okay, and here is a reference. This book, Solar Engineering of Thermal Process by Duffy and Beckman, actually it's considered as the holy book for the solar thermal. It's very advanced book. It have many things on it. And this one, which is from Caligaro, mainly from the Duffy and Beckman, but it's more easy. So because of that, we use this one as a textbook, but this is the main reference, okay, Duffy and Beckman. So whatever you have, you can work with them. This is another reference for them. If we talk about the assessment here, as you know, normal assessment will be 10% for quizzes. We'll try to make 3 or 4 quizzes, depends on the time, but inshallah, the weight of it 10% from the total weight. We have a project. I will talk about the project now. It will be 15%. And the midterm, normally in week 8 and 9, I will check the date, and then I will announce for both of you of both sections, inshallah. So here, up to now, I'm not sure how it will be. It should be face-to-face or online, but it's planned to be face-to-face, the midterm. But as I said, it depends on the situations. However, I will check, I will choose a day, and inshallah told you by next lecture or next week maximum. Okay, final exam as scheduled, and you know that is 45. For the project, we will conduct that one project, and we'll have a group of 4 to 5. Okay, you can start the working on your project after chapter 2 or 3. Okay, then you can start working it. It will be submitted by the end of the semester. No, most of you already work with the project and know how we do it. So I will send later about the project, the details, how it will be done after we work in the course a little bit. So I hope that you already know or have an idea about the course in general. This was only introduction for the course. If you want my words, it's interesting course, and it is one of the courses. We can say it is an application course because it's already an applied course. It's already the prerequisite of it, heat transfer. So most of the things that we'll have it here, it depends on the heat transfer and the thermodynamics, okay, or basic points of these two. So I hope that you will enjoy the course. Please start fresh, and wish that you will find it's easy, inshallah. I'm ready to hear from you, and if you have any suggestion, we can talk about it now, inshallah. If you have anything you want to suggest it, I'm ready to hear from
you. Doctor?
Yes.
Can we join for the project? Can we join groups from other sections?
Yes, okay, no problem. Both of the sections is already, so you can join. However, when you write just write the section, which section, if you are from section 12, the other section 11, so you can join. But please try not to be more than 4. This is the only thing. Not more than 4 students. Okay?
Okay.
I will stop the recording because it takes time to be loaded.